All right, folks. So as the board says, this video is intended for my summer students in Math 51. We're studying linear algebra. Today, during our class, we went through the first 2 pages of notes. For the sake of this video, for those students and if anybody else ever finds this video online, I'm going to sort of recap what we did on the first couple pages, just so our notation moving forward is consistent, and then any results that we've worked on, when they pop up, we can say, oh yeah, we already covered that. And then this video, I want to cover what's called the dot product. So the dot product is a way of sort of combining two vectors. And so that on our notes for the class starts on page 3 and then the end of page 4 a little bit as well. After that, then I will follow up with another video for the rest of page 4 and moving forward, which is called the cross product. So another way of combining two vectors. So I just want to sort of catch up with what we discussed already, tie together a few examples. This example, this blue vector that I drew right here, this red vector, for my Math 51 students, these are actually the homework problems. So I assigned for you guys question 6 from this homework batch. And I asked you to do part A, which is going to find the length or magnitude of each of those vectors. And I didn't ask you to do part B because that was the dot product. So we didn't cover that yet. So we'll do all that together, though. I think I'm going to go through all of question 6 because question 6 asks you to find the two lengths and then use that to find the angle between those vectors using the law of cosines. So that's actually all on page 3. So we're going to do that. So I'm going to work out the homework problem that I assigned for you folks. So if you end up watching this video before you submit this, that's okay. Just try to work it out maybe on your own, try to mimic that. And so what I'll do is I'll use these vectors then as some examples for some of the earlier lessons that we already learned. So I'm going to kind of just redo page 1 and page 2, just example-wise, state some properties based on those two vectors, and then we'll move forward a little bit already. So back to page 1 of some linear algebra. Pretty much what was covered on that page 1 was the definition of a vector, and then towards the end of it we had the a formula for the magnitude or the length of the vector. And also on that page, which I didn't write here, was what if we have what's called a scalar multiple, so a scalar versus a vector. So let me kind of just recap what a vector was. And so a vector is, according to our definition, it's an idea. It's a sort of a mathematical object that has a direction and a magnitude associated with it. So how is that different than a number? How is a vector different than what we typically think of as a number? Because we're going to have what we call scalars, which are sort of what we think of as a number. So let's say I've got something like 3 versus 3 as a vector. And so I noticed I mentioned vector notation during class today. Sometimes you'll see it bolded. So I'm not going to draw like a bold 3. I guess I could, but it's kind of a waste of ink and not really clear what I'm really doing right there. But when they type it up on paper, you might see this, something that looks like that. So sort of like a bold font indicates that we've got a vector. The other notation that we use is it's pretty much like an arrow on top, but just for the sake of writing, kind of over and up, something like that. Sometimes you might see just a bar. Different notation, different books will use different things. But anyway, what's the difference between a vector versus a sort of just a number, or what we might call a scalar? So a vector is something that has magnitude and direction. So magnitude means sort of size or length, something like that. So if I say direction, you can think of as a vector on the number line, sort of in terms of direction. And in that sense, numbers that we typically deal with, if we're envisioning it on a number line, are kind of like vectors right off the bat. So in other words, if I start at 0, if I go over 1, 2, 3 to there, then sort of the arrow that takes me there, that arrow has length 3 and a direction, right? It's moving towards the right. And if I said then what is negative 3, I might say, well, let's move to the left 3 units, right? So maybe I want to draw negative 3 in red, and I could have this arrow associated with a certain sort of direction. All right, so when we've got sort of axes, a number line or maybe XY axis, I've got that. So how is that different than just the number 3? I mean, so as a mathematical object, the concept of 3 could kind of mean different things. So if I said, how many markers am I holding right now? 1, 2, 3, right? In this sense, I'm thinking of 3 as sort of a value, but I'm not really thinking of a direction associated with that, right? I'm just sort of counting up objects. You might say, if you denoted what this means on a number line and you set it up, you might say 1, 2, 3, and kind of indicate that. So again, if you're kind of thinking of good old integers or real numbers on the number line, and you're thinking of sort of the length of that object, then you're sort of thinking of numbers as a vector. If you're sort of just counting up objects, you're sort of more towards the scalar end. So we'll keep that notation. Again, if it's typed up, you might see a bold icon or a bold digit, or else we'll have the sort of that little arrow superscript up there to mean what a vector is. Alrighty, so it's something that has direction and magnitude. So direction, so that's why we typically use arrows to denote them, because that's kind of pointing in the direction. All right, so we talked about scalar multiples of vectors as well. So let me just kind of review that in maybe a slightly different way than we covered in class. Given a vector v, so I'll denote it like that. So let me just kind of draw an arbitrary vector. Then we'll get back to this graph later. But let's say I've got something like that. And oftentimes, I can really place a vector anywhere. We talked about that in class. But if I start from the origin, that's kind of a nice little base for it. So if I draw a line, let's say in that direction, that's got a, by drawing that, that's got a length and it's in a certain direction, right? It's not going straight up. It's not going directly to the right. It's kind of rising with that sort of given slope right there. So let's say that thing right there is V. I'll just leave it in blue. I can label it, right? V as a vector. So we talked about what we call a scalar multiple. Then, what if I've got this? K times V. Okay, so V is a vector. K is not. So K is what we would call a scalar. All right, scalar versus a vector. So in this case, scalar, the reason why we call it that is it's sort of scaling it up or down. So we could talk about a scalar multiple. So this is pretty intuitive. In other words, if I said I had a vector, if this is V, what if I've got 2V? Right? 2V or not 2V? Silly. But what would 2V be? Well, if V has this certain direction and certain magnitude, then I think 2V should maybe have the same direction, but maybe twice the magnitude, right? I move V and then I go another V. Right? And so we could actually talk about sort of like V plus V once we discuss how to add vectors. But you could think of that as 2V is really V plus another V. Right? That's 2V. So here I go V, and then from the tip of that one, I attach another length of V. And so this red vector, I would say, is 2V. Okay? Same length, same direction. If I had 3V, we'd go further. So in class we mentioned if k is positive and greater than 1. So if k is greater than 1, then kv is sort of an extension of v. It's in the same direction, but a little bit long, or I shouldn't say a little bit, but longer, right, by the magnitude of k. So k is a scalar. So again, if I said I scaled it up by 2, I doubled the length. If k was 3, I'd triple the length, and so forth. So that's pretty intuitive, I think. Another case that we discussed is what if k is still positive, but less than 1? So in other words, if k is between 0 and 1, and we wrote it like this in class, if k is like that, so I'll use, let's say, 1/2. If I wrote what does 1/2 v look like, well, it's in the same direction as v, but the magnitude is getting cut in half, all right? So it would look something like that, right? Half of the blue length right there, okay? So for k being a positive value, it's either, if it's greater than 1, it's extending, right? Same direction but longer. If k is between 0 and 1, so something smaller, like 1/2 as an example, it's sort of shrinking down. And then we talked about what if k is negative. So what if I've got negative v? So if I had negative v, that would be my vector v, but in the opposite direction. So if I'm thinking of sort of a straight line, I could kind of have maybe the... maybe do sort of like a little dotted line that all these vectors sort of live along, right? Any vector that's associated with v here, if I'm going to set it up at the origin, is going to be on that line. And if it's negative v, maybe it's this length, but in the negative direction. All right, so maybe that black dark arrow I just drew there is negative v. What would negative 1/2 v look like? Well, if I had negative 1/2 v, that would be like negative v. I'm sorry, 1/2 v, the green one, but in the negative direction, right? Flipped around. So all living along that same dotted line. So I didn't write that up here on page 1, but that was on page 1 of our notes. So we've got the definition of a vector. I'm drawing them here in 2 dimensions, meaning on the plane. You can have vectors in 3 dimensions. You can have vectors in higher dimensions. But yeah, so we've got vectors, and then we've got this idea of scalar multiples, okay? And particularly the negative is sort of the same same length but opposite direction. Okay. So those were some key ideas that we covered. And then the next thing that we covered were how to combine vectors, and typically through addition and subtraction. So that's what we covered. Then the next thing that you would typically cover is multiplication, and the different methods that we're going to sort of use to define kind of like a version of multiplication for vectors. Again, one of them is the dot product in this video, and then we will move forward. All right. So on page 1 at the end there, also I talk about the magnitude of a vector. And so how do I find the magnitude of a vector? And so in 2 dimensions, it was really just the Pythagorean theorem. I want to find the length of this diagonal line. So let me label this blue vector here U. All right, and then we can start using that for our examples. This is from, again, from your homework. Question 6 gave me these 2 vectors. So they say U is 4, 2. So U is equal to... And in class with you folks, I mentioned that's... Well, let me write it like this. 4, -2. For the sake of this video, let me use sort of the triangular brackets, right? I mentioned in class that these triangular brackets are typically used for vectors. You could use parentheses, but sometimes parentheses indicate other things to my mind, so I might label the point here 3, 6. I'm sorry. Well, this will be my V later. And in red. Let's say U, I'm sorry. U is, I want to do V, rather, hold on. I told myself, rehearse this, you're recording, trying to get a nice first take. I'm sorry, from homework 6, we're going to be doing 2 of them, 3, 6, that's V. Doesn't really matter, but let's call that V, and then the red one we'll call U. I want to keep everything color-coded. So V here, as a vector, has sort of an x-coordinate, right? It moved over 3 in the x direction. It went up 6 in sort of the y direction. And so I can write it like 3, 6, sort of like an ordered pair. Now, just a note on notation. I mentioned in class, if we know we're studying vectors and we say, guys, we're all studying vectors for this unit, let's just use parentheses around vectors, then that's fine. So sometimes different notations, different books, different contexts might use different things. So if we all agree that the parentheses, we're just going to use them around vectors, then we can use that. But another common thing is to use the triangle brackets. So kind of like greater than, less than signs, right? If you're typing them, but it's those triangle brackets. And I'll use those because then we know it's a vector. That's pretty standard for vector notation. Points might mean other things. So let me just actually emphasize the difference. And since I'm going to use the triangle brackets right here, these angle brackets, technically speaking, as what we call sort of mathematical objects, the point 3, 6, and I'll use round brackets to emphasize the point, is that point in the plane. It's just a point, right? A single point. The vector is kind of represented by this entire arrow, right? So remember, the vector has length, has direction. So that's sort of why I'll use the triangle brackets, just to specify. But again, don't get scared when you see this on the homework. They tell you, they define the vector. They say, hey, V is 3, 6, and they've got round brackets. So they're just using the round brackets there, even though we've got a vector. Okay, so let me just review the magnitude formula, this magnitude formula. And so magnitude, you will see absolute value bars around the vector. Some books, or sometimes if you look online, depending, you might see a double absolute value bar, sometimes it's sort of like double bars. Again, different books, different notations, you might see that in places. I'm, for now, trying to mimic the notes that you'll see for this class, the Math 51 that we've printed out. So we're going to use sort of absolute value bars. But we can think of that as sort of the length of the object, right? The length of that arrow. And so it's the Pythagorean theorem, right? Because I'm thinking, if I don't want to mark this up, but if I dropped a vertical here, let's say, then the base of this, now I've got a right triangle. The base of this right triangle has length 3, right? So whatever the x-coordinate. The height of that triangle has height 6. And so I can do my Pythagorean theorem. So my Pythagorean theorem would say a squared plus b squared equals c squared, the hypotenuse squared. And then if I want to solve for c, I could square root both sides, right? So something that looks like that. And that's what we've got. So the absolute, the formula, let me use this notation also, right? In class, we said if I've got a vector v, maybe I'm calling the x-coordinate v1 and the y-coordinate of it v2. And so if I want to do something like that, then the formula here will be v1 squared, v1 squared plus v2 squared Okay, so V1 is sort of this length right there, right? The x-coordinate, so 3, and then V2 is that height right there, the y-coordinate 6. So this is really just Pythagorean theorem, and you've got that. Okay, so part of me doesn't want to spoil this, since I did assign this as a homework, but it's a simple enough calculation, and I'm gonna know if I want to answer the full question A at the end, which I do, talking about the cosine of the and the angle in between there. I'm gonna need to know what this is, so let's do it. So for this particular, so in other words, this formula right here, this is what we covered in general. It's just the general formula for a vector in 2 dimensions. For its magnitude, let me do it specifically for this vector v. So I would have 3 squared plus 6 squared, and then whatever the square root of that is. So that's 9 plus 36. So square root of 45. 45. Can I reduce that if I want to? So I could leave it as 45, but let me reduce that. That has a 9 in there. 9's a perfect square, so that's 9 times 5. Living in my radical, so root 9 times root 5. We can split the radical across multiplication like that, and root 9 is 3, right? So 3 root 5. So that's my length of v right there. Okay, maybe I'll make a little note of that somewhere. Length of v is 3 root 5. Alrighty. No big deal. If I wanted to do u, because I'm going to want to call that red one u, I'm going to want to use that once we establish the dot product. So let me go ahead and call that u right there. So u, from our homework, that was the one I was writing up before, is 4 in the x direction, -2 in the y direction, right? So 4, comma, -2, use those triangle brackets right there. All right, so if I want to find its magnitude now, I'll do that calculation. My red marker is not going to last me too long. Let me do it right here. And so the length of u, you can say the length or the magnitude, I won't really say absolute value, but the length or the magnitude of my vector u is going to be 4 squared plus I've got a -2 here squared, and then the square root of that. So I've got 16 plus 4 is square root of 20. Okay, and now, just like I did last time, if I'm trying to reduce a radical, what I'm looking at is the radicands, the number in there, and saying, what are his factors? Does that have any perfect square factors? And 20, has a 4 in there, so that's 4 times 5 under a radical, so root 4 times root 5, and so root 4 is equal to 2. So 2 root 5. Okay? So actually sort of nice in the sense that, I'll write that in red up top, but notice when we simplify those, they both have a root 5, so they kind of have a common little factor of that root right there. So the length of u is 2 root 5. Okay? So if you factored out that root 5, they kind of have like a 2 to 3 ratio between those two lengths right there. All right. So that's your homework problem for doing that one. But what we're going to do is once we develop the dot product, we're going to see there's sort of 2 different definitions for dot product. One of them involving a cosine of an angle. And so we can use that, and then that's what we're ultimately asked to find that angle. Let me erase, remember this dotted line, I was demonstrating sort of the Pythagorean theorem, why we're going to add the square the base, square the height. Same idea of what we did for the red here. So I came 4, you could say it's sort of like my base or ceiling or whatever of that triangle. This height would be -2, or once we square it, the fact that it's -2 doesn't really matter, right? We got that. Okay, cool. So let's think about now how to add and subtract vectors. So that, again, is mostly review of what we did today, not really being asked that on the particular homework problem that I'm working on with this picture, which was problem 6. But the next homework problem, I think I did ask you to add and subtract some vectors. So let's review that concept quickly. So after I drew that setup over there, I realized, and again, since this is review, I can throw it out there. The parallelogram that would get formed here is kind of off my whiteboard, though, right? I would end up sort of like over here, have a point over here. So let me do a rough little sketch of the scenario that's going on right here and sort of refresh our memory of how to add vectors. All right. Visually, and then we've got some formulas that we did as well. So what I'm looking at here is I've got, let's say I want to do u plus v. So here, find u plus v. So u is this, right? And v is something that looks like this. So I'm not being as careful here with the angles or the scales or anything like that. Just a rough sketch there. U looks like that, v looks like that. So what is u plus v? And so the way we can imagine this, we said in class that v, if I start moving, if I was able to lift this blue arrow off the board, move it around and put it down somewhere else, as long as it's in the same direction, so basically meaning parallel to this this given vector, if I were able to pick it up and put it down, I'm not changing its length, right? So it has the same length. If I keep it parallel, it's got the same direction. Then I could envision or imagine v living elsewhere on the board. So that's the idea. If I want to do u plus v, let me do this in black to kind of color code. Let's say find u plus v. I like to think of vectors as sort of like taking a trip. Taking a trip somewhere. So u, I was going to start at the origin and take the trip of u. So that starts me here, ends me right there, right? So if I took the trip of u, I'm at this destination. From there now I want to take a trip of v, right? I want to take a trip equivalent to this trip of v. Well, v has a certain rise, a certain run, right? So if I draw a parallel or a line parallel to v, and I'm going to do my best to do this just freehand, right? Something like that, about the same length. Then I drew it as a dotted line right there, but really if I just connect that, that's a vector right there, right? And that's basically what I like to say, another copy of v, okay? So that's u plus v. I take the trip of u, gets me here. I started here, got here. Then I take the trip of v. So what is u plus v? It's like the shortcut, right? It's like you went here, then you went here. What's your ultimate destination? I'll do this in green. My ultimate trip is I started here, I ended up here. And so that diagonal right there is u plus v. All right. Find u plus v. We did, right? Doing that in green right there. Okay. How did we do that mathematically? So for coordinates, if I guess I don't have to color code all this. If u is u1 comma u2, right? So I'm not using the vector symbol because these are just numbers. Right, but then I'm labeling them 1 and 2. It's really the x coordinate and the y coordinate, right? If u is that and v is v1 comma v2, then u plus v was this. U1 plus v1 becomes your first coordinate. U2 plus v2 became our second coordinate. Okay, so mathematically, it's nice. You add the x coordinates, add the y coordinates, that becomes it. So if you're doing that, but visually, it's that. And so what we talked about in class is we sort of talked about, I'll do this in black for now, the parallelogram formed or defined by two vectors. So what does that mean? Well, if I've got a vector v here and I've got a vector u there, then by creating the parallel up to v over here, right? In other words, start at that corner or tip, come out the same sort of length. Then if I had this up here, that's really another copy of u, right? U has this length, that direction kind of downward to the right. So a copy of u would be directed this way, sort of downward up there. That's a copy of u right there, okay? So in class we discussed the parallelogram formed or the parallelogram defined by these two guys, and that's so we've got the parallelogram. And what we said was u plus v, the new vector u plus v, is one of the diagonals right here. And so it's, if I'm starting everything from the origin, it's sort of the diagonal from the origin to the other, kind of traversing the parallelogram like that. Okay, so I think it's relatively simple to follow, to trace that path. And let's notice something here. The way I wrote it here was u plus v. So u plus v, the way I interpret that sort of trip around the parallelogram is start at the origin, travel the length and the direction of u, then from the tip, travel the length and direction of v, right? So that's my path, u plus v. And then the ultimate destination, basically, the net product of doing that is I got from here to there. So that's what the green represents. But notice, if I did v plus u, in other words, took this trip, did the v first, then from the tip of v, then took a trip in the direction and magnitude of u, I get to the same spot, right? And so what that means is the vector u plus v gets me from here to here. The vector v plus u gets me from here to here. So they're the same. Alrighty. Now, we call that property of addition has a name. That's called the commutative property of addition. And so we already know that scalars, that regular old numbers commute, right? In other words, 3 plus 2 is 5. 2 plus 3 is 5. So those equal each other. So we know that regular old numbers, or scalars we could call them, addition is commutative for them. And now we see that addition is also commutative for vectors. All right. And that's worth noting because what we may see is not every property necessarily needs to hold up. Just because things hold up for regular old sort of real numbers doesn't mean that if I've got these sort of multi-coordinate vectors that everything is always going to hold. So to note that is important, or noteworthy, I should say. Okay, before we get to the dot product, which is the new material, let's look at u minus v, how we define that. And so since we covered this together in class, but other folks might be watching this maybe for the first time, I'll sort of review it a little bit. But one thing that we noticed in class was once I formed this parallelogram, and we said the u plus v is one of the diagonals, all right? And again, I can kind of get there by either way, so it doesn't really matter. But if you envision that trip sort of around if you start from the origin, take two legs of the parallelogram, in either method, you're going to get to that endpoint. That's u plus v. What we notice then is u minus v is the other diagonal. Okay, so that's kind of cool, is that I can kind of already envision how u minus v is going to look. However, the other diagonal, remember, a vector has magnitude and direction. So yeah, I know that I could actually figure out the magnitude right now if I wanted to. I could figure out the length. But am I going to be going from this tip up to that tip, or from this tip down to that tip, right? So is this vector kind of moving upwards or downwards? That's what we have to figure out. Because u minus v is going to be it's going to be this diagonal in one of the directions. V minus u would be the opposite direction. And those are not the same, right? You can't, subtraction is not what we say commutative. You can't swap the order. If you do swap the order of a subtraction problem, you get the negative of the original answer, right? So we want to look for u minus v. So find u minus v. Okay. So we did this one way in class, where we together in class we set it up like this. I said if I want to do u minus v, we thought about it like this: u plus negative v. Okay, and we already had the conception of what a negative vector would look like from that scalar multiple. So let me do that really quickly. If I did that, then I would say start from the origin and travel u. So that's this downward. Okay, so I traveled u. Now, v is this from the origin upwards, right? Up and to the right, that magnitude. So that means negative v is down and to the left, sort of that same length. Right? So negative v would be something like that. And so now, if I want to do addition the way I did earlier, take one trip, right? Take one journey, and then at the end of that journey, start the next one. I can do that. So let's do a u, which I've drawn in red, then a negative v. So in other words, from the tip of u, travel down negative v. All right, so there's negative v. And then let's think of how we defined the sum earlier. Right, u plus v, I said travel u, then from the tip travel v, but then now do the shortcut, right? The direct route is u plus v. So here I traveled u, then I traveled minus v, and so that direct route right down there, that would be u minus v, right? Or u plus negative v, the direct route. And so I see that we're coming downward, right? And so if I see that we're coming downward, I know that it's one of these. So if I had this all to scale, this is what we did in class. I had u, then negative v was coming down here. And then I measured that, and I said, wait a minute, what if I attach those right there? Right, so that's the idea. So let me come down. Again, I know it's a diagonal based on what we covered in class. Now I see that it's coming downward, because u, then negative v is pulling it down. So this straight, that length right there is u minus v. All right, I'll just, it's in black over here, u minus v. All right. Coordinate-wise, it would be the same. So earlier I said u minus v would be u1 minus v1, right? And then u2 minus v2, I guess triangle brackets. I think earlier I went back to the round brackets, but that's the idea. So you would combine the coordinates like you would. Okay, so sort of the rule of thumb then is the way that we found u minus v is if I wanted to figure out sort of its length, and remember it doesn't have to, I can move that now. I can move that arrow over here, and as long as it's got the same length and magnitude, it's the same vector. Okay, so notice this one sort of revealed itself not really starting from the origin, right? Over here, this graph is supposed to be a new version of this. My v is coming from the origin, my u is coming from the origin, the way we found u plus v coming from the origin, right? But now the way we found u minus v is starting from up here and then dropping down here. But that's fine because we could then relocate it however we want. So the way that we found it, notice it starts from the tip of v and then goes to the tip of u. So it's different than when we added two vectors. It was like take one trip and then from that trip start another one, right? Take the trip of u, then take the trip of v. The shortcut was our sum. Here I'm taking sort of two different trips and then the distance between them, right? Or that space between the two edges becomes, or the two destinations becomes my u minus v. So the way that we describe that in, the way that I learned it kind of when I was younger, and you know, there's reasons why we see that it's downward, but basically if I'm going u minus v, go to the second one here, v, go to the tip of v, then from there get yourself to the tip of u, right? And the way that you do that, the path that you do that, that is u minus v. I like to think of that, there's a model of subtraction that called missing addend. It's actually a definition of subtraction that we teach teachers that you guys use in your Common Core. So in other words, if I want this, if I want 8 minus 5, right, let's just do a subtraction example. We know that the answer is 3. So takeaway, there's different models of subtraction. One of them was called takeaway. So if I've got 8 fingers up and I subtract 5, let's take away 5. So 1, 2, 3, 4, 5. I folded down 5 fingers and I've got 1, 2, 3 remaining, right? So that's the takeaway model. The other method of subtraction is called missing addend. In other words, let's turn the subtraction problem where the answer is sort of our answer. Let's turn it into a addition problem where sort of the unknown is one of the pieces we're adding. So in other words, I drop it down like this, the 5, the question mark, and if I add those, 5 plus what? I shouldn't say plus, equals this thing over here, equals 8. Right, so that's called missing addend. That's sort of counting up. In other words, 8 minus 5, well, let's say I start with 5. Right now I want to go 6, 7, 8, right? So how much did I have to add back? 3. So you get the same answer. This is a nice definition of subtraction right there. And I like that because that models sort of physically what we're doing with vectors. So let me rewrite this subtraction problem as a missing addend, and maybe we'll see, in other words, from u minus v, it's the vector lives between, this black vector lives between the tips of both, but where it starts and where it goes is important. Right? V minus u would be the opposite. So we want to see what's going on. So if I rewrite this, let's say question mark is the vector, is the vector that I want to define as u minus v. And I'm trying to figure out what that vector is, where it lives, where it's directed. So let me rewrite this subtraction problem as missing addend. In other words, the vector v plus some other vector is equivalent or equal to the shortcut that we call u, right? That's the idea. So in other words, what we did earlier is we said, when we added these two, we had u, we had v. So we had the red u coming down. From there we had v. And to add them, we said, what's the shortcut, right? Let's just cut the long way. Let's just get to our final destination. That's the shortcut. So what we're doing here is we want to start with a trip of v. So let's start with a trip of v. Then I want, from the tip of that, I want to add on a second vector. I don't know what that vector is yet, but I want that all to be equivalent to the shortcut of just taking u. Right? Well, u starts at the origin and gets me right here. So now v jumps me up there. From v, I have to get to the end of u. How do I do that? By following this black arrow. Right? So that black arrow right there is the question mark. Right? So in other words, let's follow that. V, whoop, plus question mark, drop down, is the same. Taking that path is the same as taking u. Right? That's what this addition problem says, this missing addend addition problem we call it. That's equivalent to this subtraction problem. And since now we identified that downward facing arrow as the question mark, now we know that that's equivalent to u minus v. Okay? So there we go. Bit of a review. I spent longer than I had imagined in my mind on that review. So what I'm going to do is I'm going to pause or stop this video. Then I will resume it immediately, post a second video, and that's where we'll start with the new stuff. So, so yes.